If you had to choose a single experiment that forced humanity to fundamentally rethink its understanding of reality, not just adjust it, not just refine it, but tear it apart and rebuild it from scratch, the double-slit experiment would be a very strong candidate. It is not the most technologically complex experiment ever performed. The basic setup is almost embarrassingly simple. And yet what it reveals about the nature of matter, light, and the act of observation is so deeply strange, so resistant to comfortable explanation that Richard Feynman, one of the greatest physicists of the 20th century, once said it contains the only mystery of quantum mechanics. Everything quantum mechanics is, everything it implies, everything that makes it both so powerful and so philosophically unsettling is present in some form in this one experiment. And today we are going to do it justice. Carefully, honestly, and without retreating into vague mysticism or false simplicity. The double-slit experiment has a long history that predates quantum mechanics by over a century. In 1801, the English physicist Thomas Young performed a version of the experiment using light. And what he found was already surprising. He shone a beam of light at a barrier with two narrow parallel slits cut into it, and he placed a screen on the other side to catch whatever came through. If light were made of tiny particles, as Isaac Newton had argued, you would expect to see two bright bands on the screen, one behind each slit, where the particles piled up after passing through. But that is not what Young saw. Instead, he saw an interference pattern, a series of alternating bright and dark bands spread across the screen. This is the pattern you get when waves overlap. When the peaks of two waves align, they reinforce each other and you get brightness. When a peak meets a trough, they cancel each other out and you get darkness. Young's experiment was taken as strong evidence that light is a wave, not a particle, and for about a century, that seemed to settle the matter. Then the 20th century arrived, and things got considerably more complicated. Max Planck and Albert Einstein's work on blackbody radiation and the photoelectric effect demonstrated that light also behaves as a stream of discrete packets of energy, photons, in ways that wave theory alone could not explain. Light, it turned out, was not simply a wave or simply a particle. It was something that behaved like either, depending on how you looked at it. This wave-particle duality was strange enough. But the double-slit experiment, when applied to individual particles, made things far stranger still. Here is where the experiment becomes genuinely mind-bending. Physicists repeated the double-slit experiment, but this time firing individual electrons, or individual photons, at the barrier one at a time, with enough time between each one that there could be no possibility of the particles interacting with each other. Each individual particle hits the screen and leaves a single dot, exactly as you would expect from a particle. But as the dots accumulate, one by one, over time, they do not build up two bands behind the slits. They build up an interference pattern. The same alternating bright and dark bands that waves produce. Each individual electron, passing through the apparatus alone, somehow interferes with itself to produce a pattern that only makes sense if it passed through both slits simultaneously. This is superposition, made visible. The electron does not take a definite path through one slit or the other. Before it is detected at the screen, it exists in a superposition of having gone through both slits at once. And those two possibilities interfere with each other, just as waves do, producing the characteristic pattern. At this point, a reasonable person might say, well, perhaps the electron really does go through one specific slit, and we just do not know which one. Perhaps if we could simply watch which slit it goes through, we would find It always takes a definite path. And the interference pattern is just an artifact of our ignorance. This is exactly the question that physicists asked. And the answer that nature gave back is perhaps the most unsettling result in the history of science. When detectors are placed at the slits to determine which one the electron actually passes through, when a measurement is made that reveals which path information, the interference pattern disappears completely. The electrons start behaving like classical particles, piling up in two bands behind the two slits, exactly as Newton's particle model would predict. The moment you obtain information about which path the particle took, the quantum interference vanishes. And when you remove the detectors and stop measuring which path, the interference pattern returns. This result has been confirmed in experiments of extraordinary precision and with many different types of particles. Electrons, neutrons, atoms, and even relatively large molecules. It is not a measurement artifact or an experimental imprecision. It is a fundamental feature of quantum reality, the act of obtaining which path information, regardless of the physical mechanism used to obtain it, is sufficient to destroy the interference. It does not matter whether a conscious observer looks at the result. What matters is whether the information about which path the particle took exists anywhere in the physical world, in any form, in any detector, in any correlation with any other physical system. If it does, the interference is gone. This is what physicists mean when they talk about measurement in quantum mechanics. Not a human-looking, but any physical process that records or encodes which path information in the environment. There is an even more striking version of this experiment called the quantum eraser, in which the which path information is obtained and then subsequently erased before the final detection event. When the information is erased in time, the interference pattern returns. When it is not erased, it does not. The universe, it appears, is keeping track of what information exists and adjusting its behavior accordingly. This has been experimentally demonstrated, and while it can be interpreted in various ways depending on which interpretation of quantum mechanics you prefer, the experimental results themselves are not in any serious dispute. So what does any of this have to do with quantum computing? The connection runs deeper than it might initially appear. The interference that shows up so dramatically in the double-slit experiment is the same quantum interference that quantum algorithms rely on to function. When a quantum computer runs an algorithm, it is, in a very real sense, setting up a situation analogous to the double-slit experiment across many qubits simultaneously. The computation explores many possible paths through a problem space at once, and the algorithm is carefully designed so that paths leading to wrong answers interfere destructively and cancel out, while paths leading to correct answers interfere constructively and reinforce each other. The final measurement then yields the correct answer with high probability. Without quantum interference, there is no quantum speed-up. The double-slit experiment is not just a physics curiosity. It is the direct physical demonstration of the mechanism that quantum computing is built upon. The double-slit experiment also serves as a permanent reminder of something that honest science communication should never let us forget. Quantum mechanics is not intuitive. It does not match our everyday experience. Our brains evolved to navigate a world of definite objects, moving along definite paths at non-relativistic speeds. And quantum mechanics describes a world that operates by entirely different rules at the smallest scales. The right response to this is not to retreat into mysticism and claim that anything goes, but to follow the mathematics and the experimental evidence wherever they lead, even when they lead somewhere deeply uncomfortable. That is what quantum mechanics has done for over a century. And that discomfort, properly understood, is the beginning of one of the greatest intellectual adventures in human history.